Good afternoon, everyone. My name is Krishna Patel, and I am a volunteer at the workshop. It's a great pleasure for me to introduce our speaker, Dr. Sonanki Keshri, who is going to talk to us about molecular dynamics simulation on GROMACS. She will discuss several aspects of MD simulations and how she used it for her research. We are very thankful to her that she really finds a way to be with us today, despite of the distance and her hectic schedule. She is graduated from Vivekananda Mahavidyalaya, West Bengal, in the year 2012. She finished her master's in chemistry from IIT Bombay in year 2014, and in 2017 she finished her PhD in chemistry under the guidance of Professor B.L. Tembe from IIT Bombay. Her PhD thesis was on ion pairs and hydrophobes in mixed solvent media by using the molecular dynamics studies. Currently, she is an assistant professor at the Department of Chemistry and Biochemistry at the Jyotinivas College, Bangalore. Her research interests include ion-solvent interaction in supercritical fluids such as water, methanol, and carbon dioxide, fullerenes in aqueous media and ionic liquids, and to understand structural properties of concentrated salt solutions. She is also selected as reviewers of many manuscripts in reputed journals from Taylor and Francis and International Journal of Theoretical and Computational Chemistry. I know about her from one of the courses running on MD simulation on NPTEL, where she and Professor B.L. Tembe explains the basics of classical molecular dynamics. So far, I try to elaborate as much as I can, but I'm sorry if I left some information about you. Over to you, ma'am.
Thank you so much for the very kind introduction, Ms. Krishna. And I would like to take this opportunity to thank all the organizers of this hands-on workshop on molecular dynamics, the entire institution, St. Xavier's College Autonomous, and Shama Ahmedabad Academy of Sciences, Ahmedabad, for giving me an opportunity to present what I know on the topic. So without any further delay, I would like to start. Yeah, I hope my slides are visible to all of you, and I'm audible as well.
Yes, it's perfect.
Okay. So good afternoon, everyone. I'm Dr. Sonanki Keshri from the Department of Chemistry, Jyotinivas College Autonomous, Bangalore. And today I'm going to speak about molecular dynamic simulations with GROMACS. Our previous speaker has already given a detailed information about what are the different type of ensembles we use, what are the different type of algorithms we use during MD simulation. So I had to modify my slide. So I'll not go into those details anymore. I'll try to explain how we perform simulation using GROMACS and what are the different type of systems we can explore, what are the different type of results we can expect out of it, and how it can be useful for different branches of science. So this is the overview of my talk. First, I'll start with what is actually molecular dynamic simulation, how to perform MD simulation using GROMACS, which is absolutely a free software, and few sample application using GROMACS, what I have done during my PhD, what I'm still doing, and my current research work. So in the year of 2013, the Nobel Prize in Chemistry was awarded to three scientists, Martin Karplus, Michael Levitt, and Ada Waschel, for their discovery of complex molecular system using quantum or ab initio methods. So this was the time when computational and chemistry really came into the picture, where they were awarded for their work in those fields. So coming into what is molecular dynamics, it's actually a digital laboratory. Why digital laboratory? Because we are not performing anything on bench. We are not doing any wet lab experiments. It's all dry in your computer, in your system. So in the real world, this could eventually mean that most chemical experiments are conducted inside the silicon chips instead of the glassware of laboratories. Turn off that Bunsen burner, it will not be wanted in another 10 years. This was told by the economist who reported on the work of 1998 Chemistry Nobel Prize awardees. According to a website on embed.org, it is actually a computational method that calculates the time-dependent behavior of a molecular system. So what we do, we try to mimic what whatever we perform in wet lab, we try to mimic the same thing in a computer to check whether those results are in accordance with what we are also getting or not. Or if we have a new system to investigate, we try to find out certain properties of those systems using different aspects of computational techniques, and then we try to compare it with experimental techniques available to check what to see whether we are close enough or not. Or even sometimes using computational methods, we can give new information which maybe is not available till now. So those are the things where really computational chemistry comes into picture. For many systems, there are still many data which are not available, which we may require for some purpose. You can easily perform using different tools, computational tools. You can get some results, you can get an idea about how the system is going to work. So before even jumping to buying chemicals and starting off your experiment, if you can just try it out in your computer to check using different tools whether it is actually going to work or not, you're going to save a lot of amount of money as well as time. So what is the basic idea behind any MD simulation? You solve Newton's equation of motion for individual particles present in your system. It may be atoms, it may be ions, it may be biological assembly. It may be solving Newton's equation of motion, basically the second law that we solve, F is equal to ma. That is, force is equal to mass into acceleration. It may be one single step for us to solve, but when a computer is solving it, when you are trying to solve this Newton's equation of motion using different computational aspects, it's actually many smaller steps for a computer. We are actually sampling conformations from a distribution, and we are not predicting what is the exact motion of the particles present in our system. There may be 10 particles in our system, there may be 1 billion particles in our system as well. So our system size can range from very small to very large. And depending on the system size, the time of the simulation also may be different. We don't simulate it for, say, the time is always measured in terms of femtosecond or microseconds or nanoseconds. So that's the time scale of simulation. Even 1 second simulation has been performed, which has taken a very long time to accomplish. Now, before we begin any molecular dynamic simulation for any system, for each and every atom in our system, there are certain things that we need to specify. First is the position of each and every atom, momentum, charge on each and every atom, and information regarding the internal geometry of the molecule. Internal geometry in the sense, if I am taking, for example, water molecule, if I want to do some study on water molecule, I need to know what is the bond length in water, that is OH bond length, what is the bond angle in water molecule, all those informations I have to provide. Even bond force constant, bond angle constant, if it has a dihedral angle. So all those information we have to provide before we begin the simulation. This is the flow chart, rough flow chart of how we perform or how we go ahead to perform an empty simulation. The first thing you can see over here is initial coordinates. Initial coordinates mean the time when we start our simulation, the beginning coordinates, X, Y, Z coordinates we have to assign for each and every atom in our system. Once we have the initial coordinates, we may not be the molecules, if we are taking, say, water only, and if we have a system, if we have a, say, box, cubical box where I have taken, say, 500 water molecules, I have randomly arranged it. So that random arrangement, it may not be the optimized structure. So what I have to do after I get my initial coordinates, I have to minimize the structure. Once the structure is minimized, once the water molecules are at a certain distance from each other where they do not repel each other, or there is a sufficient amount of distance between two molecules, we have to assign initial velocities for each and every molecule. Once the velocities are assigned, the initialization phase is over. After that, we start with the equilibration phase. Now, equilibration phase can be done in different ensembles. It can be done in canonical ensemble. It can be done in isothermal isobaric ensemble, depending on what we are expecting out of a system. If we are performing NDT, that is where number of molecules are constant, volume and temperature is constant, or if we are performing NPT, where number of molecules, pressure and temperature are constant. Once we perform equilibration in any of these ensembles, we have to check whether the temperature that we started off with, initial temperature, what we have provided, at the end also, are we getting the same temperature, or is there a huge difference in temperature? Or if we know the density of the system that we are simulating, before equilibration and after equilibration, what is the density? Is the equilibrated density matching with experimental density very close enough, or is it too far away? So all those things we check in the equilibration process. If the densities are not close enough, which is an experimental quantity, or if the temperature of the system that we have provided is not coming very close to what we started off with, that means our equilibration process is not completed. It is not done yet. We still need to process it for some amount of time. So we have to check whether our system is stable or not by checking any or by verifying any of the experimental quantities known to us. For example, in case of water, if we do, we know what is the experimental density. It's around 1 gram per cc. So after my equilibration, if I get something closer to 1, where my error bar is less, that means my system is well equilibrated. If it is not, then I need to simulate it for certain more amount of time, or there are some parameters that I have to change. So that is what we have to check, whether it is stable or not. If it is stable, then we will move on to the next phase, that is the production phase. In the production phase, what we do is we generate trajectories. All we need in MD simulation is trajectory, that is how an atom in a system is moving from one time frame to another time frame. We need their coordinates, we need their velocities and acceleration. This is what trajectory is, because it is a time-dependent simulation we are doing. So all we need is trajectory. So in production dynamics, we perform simulation for even a longer period of time as compared to equilibration. The result we get from there, the file that we get from there is known as trajectory file, that contains at every time frame, at each and every time frame, what is the position of each and every atom, what is the velocity of each and every atom, what is the acceleration on each and every atom. So based on this, we can easily calculate whatever properties we need to calculate. So all we need is the trajectory file. This is a simple flow chart of any MD simulation. While we run the simulation, the first thing we do is we assign velocities to each and every atom. Then we raise the temperature of the system. This is known as simulated aniline or heating dynamics. Once we raise the temperature of the system, then we allow the system to come back to gradually either at room temperature, if we are performing simulations at room temperature.
Sorry, Dr. Sonanki, we are losing your voice.
Okay.
Is it only us or
Is the voice?
It is only for you, I think.
Is it audible now?
Yeah, it is audible to me.
Yes, you're audible now.
Okay. So as I was saying that first we assign initial velocities to each and every atom during the course of the simulation. And we first raise the temperature. This is one way to start off our simulation. Suppose we want to perform something at room temperature, that is 298 Kelvin. We don't start exactly at 298. We increase the temperature a little bit. Then we slowly decrease the temperature to 298 and we equilibrate our system in that way. So we rescale the velocities accordingly. And during this process, we monitor the position of the atom, the bond angle, the energy that we get, or different experimental quantities that we can get. Like, as I told you, density is the one that is widely used to compare whether our system is well equilibrated or not. Once it is done, then we move on to production dynamics, where we get the trajectories. So I'll mostly be talking about the software that is GROMACS. Full form of GROMACS is Groningen Machine for Chemical Simulation. It is absolutely a free software, and it is used by many people for many different type of system to perform simulation, starting from very basic, starting from, to water system to a biological system. We can do everything using GROMACS. And there are a lot of tools in GROMACS that we can use to find out different types of properties. So it's actually a versatile package for any MD simulation. It was actually designed for different biological macromolecules that contain large number of atoms in it, but you can use it for different other type of system. You can use it for nanoparticles, you can use it for lipids, for bilayer, for any other thing. And it is a fast computing method. It has great algorithm support. It has GPU computing as well. These are the funding that is received for GROMACS, different sources which fund the entire thing of GROMACS. So all my work, whatever I have done in my PhD, as well as what I'm doing now in my research area also, I use GROMACS because, first of all, it is free. It can easily be installed in any system, even in Windows, it can be installed. It can be installed in Ubuntu. So I can work with this anywhere, anytime I can work with this. So this is very much user-friendly as well. And as I told you, the system size in case of GROMACS, it varies from very small molecules like ions, starting from hydrogen or helium, to large biological macromolecules, say protein. So there is a wide range of system that we can study using this software. So this is different type of system size and different type of, as a function of simulation time, different system size is given. So for ab initio and quantum mechanics, what's the system size we can see. For atomistic and molecular modeling, which is what I'll be focusing on, the system size, we can see what is it and how much time is required for simulating this type of system. Similarly, you have dislocation dynamics, mesoscale continuum simulations, different type of engineering components. But my work, and I'll be focusing mostly on atomistic and classical molecular modeling. So now I'll move on to some sample applications. So before I go to any sample applications where I will show different type of systems that I have done or I have worked using this software GROMACS, there are certain terminology that needs to be known, that what are the things we are looking for or what are the results we are looking for. We can get any system, we can do a simulation and get the trajectory, but what is the use of it? Or the results that we get from simulation, we need to know that where is exactly we are going to use it. So there are certain results that we get that we can directly compare it with experimentally available quantity. One such thing is potentials of mean force. And in order to study thermodynamics of associations in either an ionic system or hydrophobic system or any other system, we compute potentials of mean force between solute molecules as a function of intermolecular separation, using constrained molecular dynamics method. Constrained method means, as you can see from this image over here, there is a plus charge written on this and there's a minus charge written on this. So we are assuming that this is an ion pair. Any ion pair, it can be as simple as lithium chloride. The distance between the positive and the negative ion here, I have taken it as 0.2 nanometer. This is just an example to show what potentials of force is. Now, what we do, what is exactly potentials of mean force? We calculate it between two different solute molecule as a function of intermolecular separation, that is the distance between the plus and the minus ion, or distance between any two solute molecule using constraint. This distance, what we are fixing as 0.2 or 0.9 or 1 nanometer, that is why it is known as constraint. If we are not assigning any distance between the two solute molecule, that means it is an unconstrained MD, where we are not forcing the two solute particles to be at that particular distance. Now, once we have the solute molecules at a particular distance, what exactly is PMF? Potential of mean force is actually free energy of bringing two particles close together in a solvent from a large original distance apart to a separation R from each other. So first I will show you how to calculate potential of mean force. So for that, first we'll assume that we have taken an pair of ions inside a box. Next, we have fixed the distance in between them at 0.2 nanometer, for example. Then we are going to place some solvent molecules around the ions. So this around the ions, this white and red ball stick, they are all solvent molecules. Now what we will do, we will allow the solvent molecules to move around the ions, because we are doing an MD simulation where the atoms are constantly moving. So we'll allow the solvent molecules to move around the ions. As and when the solvent molecules move around them, there are two different types of force that will be acting on the ion. The first one is the direct force between the plus and minus, or plus and plus, or minus and minus, or if you have neutral particles between them, there will be a direct force acting between them. The other one will be the ion solvent force acting between the ion and solvent. This is one for the solvent molecule. You will have ion solvent force acting as well. Now, there are other solvent molecules present as well. You have not taken only one, but you have taken many solvent molecules in your system. So they will also exert same type of ion solvent force on the ion. So therefore, by adding the ion-ion direct force and the averaged ion solvent force, you will get the mean force acting on this particular pair of ions. So how you do? Mean force is actually direct force, that is this, plus average of all the ion solvent force that is exerted on the ion pair or exerted between any two solute molecule. Now you have calculated the mean force at 0.20 nanometer. What you want to do after that? After that, you have to calculate it at several distances. At 0.2 only, if you calculate, you will get one data, but that is not enough for the calculation. According to the definition, it is potential of mean force is a force or potential that will act between two ions when you want to bring any two system from very far distance to a very close distance. So we need to have a range of distances here where you are going to calculate mean force. So now suppose you calculate at 0.21 nanometer. Then you calculate the mean force at 0.22 nanometer. Then you go on till calculation till 1 nanometer. Here I have given example till 1. You can go till 2 nanometer as well, depending on the type of system that you take. Again, if you take very small system, that if your plus and minus charges that is shown over here is for ion pairs only, that is for alkali or alkaline earth, metal ions and all, distance that you start off will be dependent on the size of the cation, size of the anion you take. Now, instead of sodium and chlorine, or instead of lithium and chloride, if you move on to two methane molecules, you will not start with 0.2 nanometer, because you have to see the radius of the methane molecule as well. So depending on the size of the solute, the distance that you start off with and the distance that you end will be different. So this, I'm giving you an example for very simple ion pair. So I've started with 0.2 nanometer and I'll continue till 1 nanometer at an interval of 0.01, and I'll calculate mean force at each and every distance, similar to what I had done earlier. Now, once I have calculated it, what we have is actually ion pair distance. We have the mean force. So what we do now, if you integrate the mean force, you get the potentials. And since the potentials that you get is obtained by integrating this mean force acting between these two ions, it is known as potentials of mean force. So this figure over here, it shows two ions coming together in water. So this is how potentials of mean force is calculated. And this is the overall formula that we use. That is WR is equal to WR naught minus integral of R naught to R FR dr plus 2 kT ln R by R naught. Out of all these three terms that you are seeing over here, this integral of FR dr is what the mean force integration is. The first term is calculated based on the dielectric constant of the medium that you are taking. And the last term takes into account entropic contributions that you face during the simulation because your ions are constantly moving. It is not placed at a certain position. They're constantly in random motion. Now, after you get the potential of mean force, how do you analyze the graph, or what do you expect from the graph that you get? This is how a normal graph, normal potential of mean force graph look like. It is PMF versus distance between any two solute particles. So this figure over here is showing the PMF of two ions which are coming together in water or any other solvent. It shows how solvation shell of any solvent molecules are structured at different ion pair separation. This distance over here means that this is one distance between the two ions. This is another distance between the two ions. And you can see there are several minima and maxima. The first minima that you can see over here at the shorter interionic distance, this is known as contact ion pair or contact separation. What is a contact separation? Where you can see the plus and minus charges are together. There is no solvent molecule that is coming in between them. Not even part of solvent molecule. So that is why it is known as contact ion pair or contact separation. The second minima that you see over here is known as solvent assisted ion pair. What is solvent assisted ion pair? A part of the solvent molecule only will come in between the solute, not the entire solvent. It's only a part of the solvent that comes in between. The third one that you see over here at slightly higher interionic distance is solvent shared ion pair. What is it? Where one solvent molecule is coming in between both the ions, where one solvent molecule is actually shared by both the plus and minus ion. And the last minima that you observe at a very higher interionic separation is solvent separated, where both the ions have individually formed their solvation shell. Now, extensive computer simulation shows that the shape of this PMF curve, it depends on various factors. What are the various factors? It depends on density of the solvent. It depends on, solvent composition. It depends on size of the ion. It depends on temperature and pressure at which you are doing your simulation. It also depends on concentration of the medium or concentration of solute that you are taking. Although there are several other factors as well which determine the association of any solute and solvation structure, but we are going to focus here on these five factors, and we'll see to what extent these factors affects the solvation structure. So this is the same picture: contact ion pair, solvent assisted, solvent shared, and solvent separated configuration. These are the four configurations that we expect to get when we carry out any molecular dynamics simulation using constrained molecular dynamics approach. Now, it may be that in some case you get only 2 of the structure, in some case you get all 4 of them, depends on system to system. So first, then I'll just give you a brief I'll go through the computational methodologies that I have used throughout my work. So all the applications that I'm going to show you now I have performed using classical molecular dynamics in order to study the structure and dynamics of either ionic or neutral or hydrophobic solutes using the GROMACS package version 4.6.4. This is very important to mention the package number whenever we are using any software. And the basic input to any classical MD simulation is the coordinate, initial coordinate that we give to each and every atom. The initial coordinate and the force field. So the coordinates are generated using the software PackMol. Again, it's a free software available. The bond length, the bond angle of the molecules, of the solute molecules, of the solvent molecules that we take, they are kept constant throughout the simulation using either of these 2 algorithms, either shake or lengths, depending again on your system. The equation of motion, because we are integrating Newton's equation of motion at each and every step. So we have used over here leapfrog algorithm, but there are many other many other algorithms available to integrate Newton's equation of motion. And all my simulations are performed in the NPT ensemble, that is where number of molecules are constant, pressure is constant, and temperature is constant. So number of molecules I have kept constant using periodic boundary conditions, where the box is replicated along the 3-dimension. Constant pressure is maintained using Berenson barostat. Constant temperature, I have used the velocity rescaling thermostat. So now first I'll discuss the effect of density or effect of solvent density on ion pair association, how it affects the shape of the potential of mean force curve that I had just shown you. So this is the system to study the effect of solvent density. So simulations were performed with one single sodium chloride ion pair in supercritical methanol. What is supercritical state? It is beyond the critical state where you cannot distinguish between a liquid phase and a vapor phase. And supercritical solvents are assumed to be green solvents, apparently. So I have taken one sodium chloride. I have fixed the distance between sodium plus and chloride minus. I started from 0.2 nanometer. My solvent over here is supercritical methanol. The force field that I have used is OPLS for methanol, that is optimized potential for liquid simulation, and Smith and Dank's potential for the ion pair. So I have done it along 3 different isotherms with different densities. So the temperatures I have used is 523, 623, 723. Why I have chosen this temperature? Density was experimentally available at these temperatures. So I will get to know during the course of my simulation when I equilibrate my system that whether I'm getting the correct density, whether during my equilibration I'm getting the correct density or not. If my density is correct, matching with experiment, I can say that the force field that I am using for this particular system is actually correct. If I'm not getting the correct density, it is not matching with experiment, then I need to have a check with my Forcefield parameters also. Forcefield parameters, what are they? I'll explain it in details during the workshop time. So this gives me a better check on the Forcefield parameters that I use. So luckily in my case, in this case, OPLS and Smith and Dank reproduce the densities perfectly. Based on the density of the system and based on the what shape of box you want, I have calculated the number of solvent molecules to be taken. As you can see, depending on pressure, depending on density and temperature, the number of molecules are also different. And these are the dielectric constant of supercritical methanol that I have calculated it using GROMACS. So this is my entire system under study. Once I have this system at every density, I have calculated potential of mean force between sodium and chloride ion pair, starting from 0.2 nanometer till I have gone to 1 nanometer. So this is the PMF between NaCl ion pair in supercritical methanol as a function of density. As you can see, the black one, that is the bottom one, is at the lowest density 0.040, whereas the top one represents a PMF at the highest density 0.563 grams per cc. Now, here you can see that the first minimum and the second minimum, actually, it reflects the geometry and stability of different ion pair configuration. The first one is a very deep minimum. It is the contact ion pair, where both the ions are in contact with each other. The second minimum is present, but not in a very greater extent. You cannot call it as a proper minima also. So this minima is solvent shared ion pair. And the position of this minima, as you can see, it is not shifting either towards very left or towards very right with density. The position is fixed up around 0.2 to 0.21 nanometer. The minima in the CIP state, it tends to be deeper and deeper with decreasing density, which indicates that the contact configuration, it becomes more and more associative at high temperature and low density condition. Now, this is the PMF of sodium chloride ion pair at room temperature. You can clearly notice the difference between these two. At any given density over here in supercritical condition, you do not see three minima like that. Whereas in ambient condition, as you can see, the minimas are very distinct. 1, 2, 3, and 4. All the 4 minimas are very clear. Also, the depth, if you see, contact ion pair over here, if I take it to be roughly around minus 30 to 32 kilojoules per mole. Whereas here, it's all beyond minus 100. So there's a huge difference in the value of potential of mean force that we get in supercritical condition if we compare it with the ambient condition. So why is that? First of all, the interaction between the two ions are much stronger in supercritical compared to room temperature. This is mainly because of the dielectric constant in supercritical methanol. The dielectric constant in supercritical methanol is around 1.61, which is way smaller than what is the dielectric constant in ambient condition. For ambient condition, in case of water, the dielectric constant is 32. So you can imagine the difference, 1.61 and 32. And dielectric constant does affect association of ion pair. In case of ambient condition, there are 3 different distinct minima you can observe. Whereas in supercritical condition, it is not the minima that you get, the second one, it's more of an inflection point. And that too, you get it only at higher densities, not at lower densities. The higher stability of the contact ion pair is attributed actually to the lower dielectric constant of supercritical methanol. The strong association between sodium and chloride, it prevents them from dissociating into bulk, and hence it reduces the possibility of any other configuration formation. And because of lower dielectric constant of solvent, it cannot pull apart the ion pairs very far. It cannot do that, which it can do it in ambient condition. So that is why the difference is so much. Now, how you can also calculate from here, what is the contribution of different thermodynamic parameters to PMF? What are the different thermodynamic parameters that you can calculate? Like, what factors affect the formation of contact ion pair? Is it driven by entropy or is it driven by enthalpy? So that also you can calculate if you know how to calculate PMF. So what is PMF? As I told you, it is a change in free energy to bring two solute molecules close together from an infinite distance to a certain distance r. And if you are performing your simulations in NPT ensemble, that is, number of molecules are constant, pressure is constant, temperature is constant, then Potential of mean force, that is W or R, it is analogous to Gibbs free energy. Whereas if the simulations are done in NVT, it will be analogous to Helmholtz free energy. And by decomposing this PMF into an enthalpic part and an entropy component, you can determine the relative roles of entropy and enthalpy in ion pair formation. This will give us further insight as to what is driving the two ions to come so close to each other and to give you such a high value of PMF in supercritical condition. This will give you a very clear picture about it. So delta G, as we know, is equal to del H minus T delta S. So we are going to use that formula. So this is done using finite temperature difference method. What is finite temperature difference method? Where you calculate PMF at 3 different temperatures. So one you are doing, suppose here, if I go back to the system under study, I have done one in 520 at 523 Kelvin. So other two I will do at relatively lower temperature than 523. The other one I will do at relatively higher temperature than 523. Possibly what the temperature difference that we take is plus minus 30 Kelvin. So one is minus 30 Kelvin and one is plus 30 Kelvin we take. So if you do that, then this is the formula we use. So delta S will be calculated based on 2 different delta G. And once you get the delta S value, you can substitute it in this equation known to all of us from thermodynamics. We can get the value of delta H. Now, if we perform this for the system that I have studied, this is what I get. So this is under supercritical condition and this is under ambient condition. And this shows the relative contribution of entropy and enthalpy to PMF in ion pair formation. So the blue one is the PMF, that is delta G. The red one represents enthalpic contribution and the black one represents entropic contribution. As you can see that in both the cases, your entropic contribution is much higher compared to your enthalpic contribution. So you can say that entropy is the factor that drives ion pairing, whereas enthalpy is the one that opposes it. Now I'll try to explain you why. You see that enthalpic contribution is flat at most of the ion pair distances, except for relatively smaller distance. Now, when contact pairing happens, that means where both the ions are together. At that point, when you are bringing the two ions from very far to close, very far means where both the ions have their proper solvation shell. From that point, you are bringing the ions close to each other, where you are removing solvent from the ions. So what is happening during the formation of contact pairing or contact configuration? Solvent molecules are released from the solvation shell to the bulk, because of which the attractive interaction between solute and solvent molecules is lost. And during this, very high amount of energy is required to restore the newly released solvent molecule to its rotational, vibrational, and translational degree of freedom which exists. And this, the absorption of this required energy, it comes from the surrounding solvent molecules, which result in very high positive value of delta H. Also, during the process of contact configuration formation, when solvent molecules are released in the bulk, it increases the entropy of the system. So entropy favors contact pair configuration in both supercritical as well as in ambient condition. So knowing what calculation of PMF can give you better insights into how a contact configuration is formed, and that is this contact configuration you can check in case of very simple ion pairs from to nanoparticles to protein molecules to any biological assemblies as well. It will give you a detailed insight. From PMF, now what are the other factors you can calculate? So the second factor that affects the shape of potential of mean force is the solvent composition. This one I had shown you only with supercritical methanol, that is pure solvent I have taken. Now, if you take a mixture of solvent, what will happen? So there are two different studies I have done in supercritical conditions only I'll show. One is NaCl only in water methanol mixtures. Other one is NaCl in water carbon dioxide mixture. Now, the basic difference between the two binary mixtures taken over here is one is a polar mixture, whereas the other one is where one component is polar, the other one is non-polar, that is water CO2 mixture. So where we can see both the effects, where you have a mixture of polar solvent, where you have a mixture of polar and non-polar solvent. And we have taken NaCl only as the solute. And all the simulations, all the results that I'm going to show you now is that it will correspond to infinite dilution. Infinite dilution means you have large number of solvent molecules, but the number of solute molecule is only one. So compared to that 500, 600 solvent, you have only one solute. So that is what is meant by infinite dilution. And densities I have matched with all the experimental results to validate the force field that I have chosen. So this is the polar binary mixture where water and methanol is solvent number 1 and solvent number 2. Sorry, there's a mistake over here. The solvent number 2 will be methanol. The solute is sodium chloride. The temperature is 623. The pressure is 350 bar. This is the experimental density. And this is the dielectric constant calculated from simulation. This corresponds to polar non-polar mixture where my solvent number 1 is carbon dioxide, solvent number 2 is water. So polar and non-polar mixture. Now, how is the PMF different? This is the PMF we get if we take a binary polar mixture, and this is the PMF we get if we take a polar non-polar mixture. So the figure in the left-hand side shows the PMF of NaCl ion pair in water methanol, and in the right-hand side, it is in water CO2 binary mixture. In both the cases, you can see that one deep minimum is observed here and here, which corresponds to CIP, which is followed actually by an inflection point rather than a minimum. And that inflection point you can see clearly in case of a polar mixture, but not where you have carbon dioxide as one of the component. Now, interaction between the two ions, it shows a progressive increase as the methanol or carbon dioxide content increases in the mixture. This, of course, is not surprising in the view of much smaller dielectric constant of both methanol and CO2 under supercritical condition. So the dielectric constant of the solvent mixture decreases with increase in mole fraction of either carbon dioxide or methanol, and hence it results in weaker solvent-solvent and ion-solvent interaction. So lower dielectric constant of solvent, it cannot screen the ion pair effectively, and that brings about an increased ionic association at supercritical condition. This is what I have discussed earlier also. Now, as methanol CO or CO2 mole fraction is increasing, the density of the solution is also decreasing. And there are less number of solvent molecules to pull apart the ion pair. So that also decreases the magnitude of force exerted by solvent on the ions, and hence it increases ion association. What is surprising to note here is between these two graphs is NaCl PMF in pure carbon dioxide. It looks, if you can see here, this brown curve, it more or less looks like an LJ potential. There is no inflection point at all, just one deep minimum. So it more or less, it looks like pair potential in if you do a vacuum simulation. Vacuum simulation means where you don't have any solvent, only between the two ions you calculate direct force. This is exactly how you get the PMF, Leonard-Jones potential. So in pure non-polar solvent, your potential looks like that. Now, when you have a mixture of two solvents, there is one more thing that you can consider. That when you have two different solvents, say water methanol, water DMSO, water acetonitrile, water CO2, both the solvents will compete to be around the ions, plus or minus, or any hydrophobic solute. Now, which solvent will be attracted more towards the positive, which will be attracted more towards the negative? Which of the two solvents will solvate your ion pair preferably over the another? So this is known as preferential solvation. So when you have solvents of different polarity, it is important to know which one is being solvated by which solvent, which is actually known as preferential solvation in a competitive environment. How do you do that? We study it using density profile of solvent molecules around the ion pair. That what is the density of each solvent around each ion pair. So this is how your graph will look like. If you have the trajectory file after your simulation, with the help of that, you can actually easily calculate this type of graph. This is also done using GROMACS. So this is your plus charge, minus charge. This is done at contact configuration. This axis will give you density. Different color codes are there for indicating density of solvent molecule. And this layer will give you an idea about how many solvation layer that particular solvent forms around the ion. So this is the solvent density of water. This is the solvent density of methanol around the ion pair. And this is in the non-polar mixture. This is again around water. Sorry. And this density profile is around of carbon dioxide around the ion pair. So this is the density profile as I have told you. Now you can see that in case of water methanol mixture, both the solvents are contributing to the formation of the first solvation shell. But if you compare in terms of preferential solvation, it is both the cation and the anion are preferentially solvated by water as seen from this density profile value. You can see here it is maximum is 133, here it is 56 nanometer cube. Whereas in case of a polar non-polar mixture, the picture is completely different. Density of water molecule around the ion is much higher compared to carbon dioxide. It is not even forming a proper solvation shell, as you can see from here. Whereas here there is proper solvation shell forms. Spherical shell is formed over here. Density is 157. Here it is only 16.8. So CO2 does not even form a clear-cut solvation shell. So you can say that both the cation and the anion are preferentially solvated by water molecules in the entire composition range that we have studied. And an important thing to observe here is, unlike water methanol mixture, that is unlike polar solvent mixture, where both the components contribute to the formation of first solvation shell, CO2, which is a non-polar solvent, it does not contribute to the formation of first solvation shell in water CO2 mixture, even if your percentage of carbon dioxide is very high. So it's always the polar solvent that contributes more compared to a non-polar solvent. The next effect is of effect of ion size. If you take different size ion, you are going to get different result for different type of ion. Even for hydrophobic solutes, if you start from say methane, then you go to ethane, propane, neopentane and all that. So all those solutes will give you different results for association. So size of the solute plays a very important role on the shape of the PMF that you get. So in order to do this, I have taken alkaline earth metal halides in supercritical water in a pure solvent. This is the system under study. This is the temperature at which I had studied. 250 bar pressure, density was 0.17, which is experimental. Based on the density, based on my box type or box length that I have taken, I've calculated the number of solvent molecules. And this is the dielectric constant calculated from simulation. And these are different combinations that I have taken. So I've taken all the alkaline earth metal ions and I have taken all the halide ions. So I've taken all the possible combinations. So there are 16 different systems that is studied over here. And for all the 16 different systems, I have studied potential of mean force. First thing is that potential of mean force exhibit different shape based on the ion size that you have taken. Now here, I'll show two different PMF. One is a series of PMF of 4 different cation paired with a given anion. And the other one is different anions paired with a given cation. I've taken magnesium in this case. Certain general trends are there that are very clear from the picture only if you see. First, of course, The contact minimum, it shifts to larger interionic distance with increasing ion radius, which is very obvious. You increase the size of the ion, your contact configuration is going to shift. Second, the contact configuration is more stable for the smallest ion. Why? Because the smallest sized ions, they have the highest charge density associated with it. Also, ion-ion contacts, it become less stable. That is the CIP, contact pair configuration. The stability becomes less and less as the size of either the cation increases or the anion increases. With difference in size of cation and anion, same size cation and anion, if it is there, the interaction will be much more stronger compared to if you take a very large size cation and a very small sized anion, a very large different two sides of solute. That I'll explain it in further detail using Colin's law of matching water affinities. Now here I have taken three different PMF for three different ion sizes. So we have analyzed the solvent structuring about representative, small, that is magnesium and fluoride, large, that is barium and iodide, and small, large, that is magnesium and iodide. So three different representation I have taken. This, according to the figure shown here, CIP state has a lower minimum than the solvent separated or solvent shared state. In magnesium fluoride, that is the black curve, and barium iodide, that is the blue curve. Whereas solvent separated configuration is deeper than the CIP contact configuration in case of MgI2, that is the red curve. Now, here is the explanation that I'll provide from the simulation. As ions move far apart from each other in any solvent medium, there are different energetic components that contribute to the overall shape. First is the direct electrostatic interaction between the ions that will weaken. Second, there will be some favorable solvent ion interaction due to the added water molecules that enters the space between the ion. But third, there will also be an unfavorable interaction due to orientational restriction of first shell solvent molecules beyond the restriction they would have had in the bulk. Now, why is the CIP state more favored to solvent separated or solvent shared when both the ions are small? Of course, the electrostatic interactions are most favorable in the contact state because ion-ion separation distance is very small. In addition to that, the structuring effect of water also stabilizes the contact state. When you go to a state where both the ions are of large size, like barium iodide and all, the difference in direct electrostatic interactions between contact and solvents shared, that is small, and the water cage structuring effects are also quite small. Most of the change due to ion pairing of barium iodide, it occurred due to hydrogen bonding network of the surrounding water molecule. And in case of large ion pair, both the ion solvent as well as the ion-ion interaction, they get weakened. Around large sized ions, water molecule will start forming hydrogen bond with other water molecule as they would do around a nonpolar solute. Pairing of larger ions enthalpically stabilizes the surrounding hydrogen bond network, and hence contact pair becomes more and more stable. Whereas if you go to magnesium iodide, where one is very small, the other one is very large, contact ion pair is less stable than the solvent. So the second minima is more stable. Now the main contribution to this difference is coming from the force from solvent molecules. There is an asymmetric packing between the small size magnesium and the large size iodide ion, and hence the surrounding solvent molecules will try to push them apart, which will make the contact pair less and less stable. The smaller ion will attract a water cage around it for different electrostatic reasons, and the larger ion will be compatible with a water cage for hydrophobic reasons. So here hydrogen bonding, it will play a very important role as to which configuration will dominate and which will not. And these results are actually in accordance with Colin's law of matching water affinities. So how does hydrogen bond help over here? This is the general definition of hydrogen bonding in case of water that we use in case of any system, be it pure solvent, in presence of solute, in macromolecules, in presence of protein molecules, that the distance between OH should be smaller than 2.6 angstrom. The distance between two oxygen atoms should be smaller than 3.5 angstrom, and this bond angle should be smaller than 30 degrees. This is the geometric definition that is used. And these are the number of hydrogen bonds that we observe, that we have calculated in the solvation shell, first solvation shell of the cation and of the anion. So as you can see, with increase in size of the anion and the cation, the number of hydrogen bond in the first solvation shell, it is increasing. Now, if you put an ion in water, what will happen? In the ion's first solvation shell or first hydration shell, water molecule will adopt different type of structure depending on the size and the charge of the ion. You can use hydrogen bond to explain the changes that happen in the water structure around ions of different sizes. The effect of ion on the structural properties of water, it can be explained by a competition between ion-water interaction that is governed mostly by charge density effect, and water-water interaction that is governed by hydrogen bonding effect. So these are the two competitive effect that goes on when you take ions of different sizes. Now, when you have smaller ion, which are commonly known as cosmotrophs, they cause strong electrostatic ordering of neighboring water molecules because their charge density is so high. And so hydrogen bonding network in water will be significantly perturbed. Whereas in case of large ions, which is known as chaotrophs, because their charge density is very low, the attraction between water and the ion will not be that strong, and the tetrahedral network of water will not be affected that much. So the neighboring water molecule will mostly be hydrogen bonded. So in case of small ions, the water molecules are electrostatically ordered. In case of large ions, it is hydrophobically ordered. So because due to this, we can explain the difference in contact configuration, stability, and solvent shared configuration stability. What is the factor that is responsible for higher stability of one configuration over the another if you change the size of the ion. This hydrogen bonding also you can either directly calculate using GROMACS tool, or you can also write a code for it. Writing code for hydrogen bonding is very easy to calculate how many hydrogen bonds are formed in the solvation shell, in the bulk. Solvation shell means first shell of the ion. Then in the bulk, how many are there? It is better to write a code than trusting the GROMACS hydrogen bond numbers, because the number that we get from the GROMACS software is not always very accurate. Next thing I want to show how concentration of ions or concentration of solute affects PMF or shape of the curve, potential of mean force curve in ambient condition, that is at room temperature, and at supercritical condition. So several studies have reported the effect of solvent composition, ion size, force field parameters on ion-ion PMF in supercritical condition via constraint method, that is where you fix the distance between ion. But when you move on to ionic solutions at finite concentration, that is when at least several number of ion pairs are present randomly in a solvent. As you can see here, this white and red smaller one is the solvent molecule. The blue sticks and the cyan color sticks, they are all ions. So there are more than one ions present in this solution. And they are relatively less studied in using computer simulation and solvation. In these type of system, they may proceed in a very different way compared to that in dilute solution, because your solute molecule, that is this bigger size balls, blue or cyan colored balls, they may be present as clusters compared to single ion. So whenever there is clustering effect observed in any solution, it leads to further complications. So here what we have taken, two different studies have been performed using for concentrated solution using alkaline earth metal as well as alkali metal. So as a combination, I have taken all the alkaline earth metal chlorides in supercritical solvent and at room temperature also. I have fixed the number of molecules as 1000. I have changed the number of cations as well as the number of anions. Since it is a alkaline earth metal halide, so if your cation number is 5, you're taking your number of anions should be double of it. So based on that, this is my smallest system size and this is the largest system size. And I have calculated molality based on the number of solvent and number of water molecules that I have. And this is how my graph looks like as a function of molality. This is the experimental molality I have calculated, and I have cross-checked it with simulated molalities also, and it matches quite well. Now, this is the PMF that we get in supercritical condition. This is the PMF that we get in room temperature condition for different concentration, different molalities. And these PMFs, both in room temperature as well as in supercritical condition, they are all characterized by 3 minima in both the conditions. The striking feature of the PMF plot is that the stability of CIP, that is the contact configuration, it increases with a decrease in salt concentration in supercritical condition, whereas the opposite is observed in case of room temperature. So rationale for the higher stability of contact configuration with decrease in salt concentration in supercritical condition that I'll give you after I show you the cluster size distribution, how clustering is happening in both the condition. One more notable feature of the PMF is that in ambient condition, first transition state, as you can see here, this point, it is not easily simulated when the concentration of salt is very low. We don't get the data in between. As you can see here, there's a gap, and it happens only at lower concentration. Why it happens? Because when you have very few number of ion pairs, it is difficult to get good radial distribution function from simulation because of poor statistics. It is not possible to obtain PMF over a wide range of distances. But the moment you shift to room temperature to supercritical, with an increase in temperature, this discrepancy is not observed anymore. You get a smooth curve. This is because the higher amount of thermal energy that is available in supercritical conditions as compared to those in ambient condition. So with rise in temperature, with increase in temperature, the movement of the ions increases too fast, and because of that, it results in covering all the distances corresponding to ion pairing. And the increased stability of all these configurations in supercritical condition compared to ambient condition is because of the decreased dielectric constant. As I have given you in this table, you can see the dielectric constant values. 0.27 molality at room temperature, it is 61.8, whereas in supercritical, it is 3.58. Such low values you get in supercritical condition. Now, you also form, there's a hydration shell formed by water molecules around the ions, and these high water molecules or these solvent molecules, it screens the charges of the ions. And because of this screening effect, it significantly attenuates their Coulombic interactions with each other. In ambient conditions, the ions are screened from each other by water molecules to a larger extent because of the high value of the dielectric constant. In supercritical conditions, when you move on, the hydrogen bonding network between solvent molecule is perturbed to a very significant extent. The hydrogen bonding in solvent exists only 1/3 of what exists at room temperature. And because of this, the electrostatic interaction between the ions become much more stronger than the force acting between the ion and water or between solvent molecule. And hence the ion pair cannot be screened effectively by solvents having lower dielectric constant, and that is why the ion association is strengthened. And hence electrolytes or any solute molecules for that purpose, they tend to associate at higher temperature and lower densities. As a result, all these configurations are more stable compared to those in ambient condition. Now, you can see in supercritical condition, the decrease in dielectric constant facilitates ion association. So you may say that contact ion pair is supposed to be more stable in 5.55 molality solution, but in reality, you observe the opposite scenario over here. Why? Because there is hardly any decrease in the dielectric constant as you move on. It is from 3.58 to 3.30 only. And this, if you do simulations for a very long time, this differences may be further lowered on. So in case where you have more number of ions, concentrated solution, supercritical solvent, dielectric constant of the solvent is not playing a significant role providing stability to the contact ion pair. So what is it that is providing stability when you have more number of ion pair? So that answer will be given by clustering effect. What is clustering? This is the clustering clusters that we get.
Excuse me.
Yes.
Excuse me, madam. Yeah,
Yes.
5 more minutes we have.
Yes, sir. Yes, sir. I'll do 5 minutes. So this is the clustering effect that we observe in case of a supercritical condition for the highest concentration, and this is what we observe at room temperature. There is a clear difference between these two pictures. First of all, how do you define a cluster? It is a set of ions with each ion connected with at least one another in the same cluster, regardless of the charge and species. It is not like only plus has to be connected with minus. Plus and plus can be connected, plus and minus can be connected. So two ions are considered to be connected if they are separated by a distance smaller than a certain cutoff distance. Now, in supercritical conditions, as you can see, there is a strong dominance of very large size of clusters and distribution of cluster size. It is much more wider. This is the cluster size distribution in supercritical condition for different concentration. This appears as you change the concentration to higher one, it appears more like a Gaussian type of distribution. And clusters of different sizes are formed in higher concentrations, ranging from 50 to 250 size of clusters, which may lead to higher stabilities of CIPs with an increase in concentration. But these clusters rapidly interconvert into one another. That is, there is a continuous redistribution of cluster size in supercritical condition, which is also evident from the snapshot which I had shown you earlier. In lower concentration, as you can see, the ions have tendency to form one single cluster comprising of say 12 or 8 or 9 ions. So that is what results in higher stabilities of CIPs in such solution. If you go to room temperature, this is what the distribution looks like. So even if the density is increased, it is only dominance of certain cluster size that is there. The ions tend to remain more or less as a single ion compared to cluster. Only for the highest concentration, cluster size of 11 dominates. Other than that, at lower concentration, it's a single sized ion that dominates. Now, if you look at the distance between the ion pairs in lower concentration, higher concentration, at both supercritical and room temperature, you can see that as a function of time, this is the distance between calcium and chloride at room temperature supercritical. At lower concentration, this is at the higher concentration. So if you can see that it is very clear distance between the ion pair is fixed at around 0.27 nanometer. It hardly shows any change at 0.27 molar solution at supercritical condition. There is no change, this red curve. Whereas the black curve, it fluctuates a lot. So this indicates that ion pairing in supercritical condition is favored in low concentrated solution, whereas in ambient, it is favored at high concentration. Whereas the interionic separation, it shows a large fluctuation from equilibrium distance in case of ambient condition for 0.27 molar solution, which suggests that they are far apart from each other and no ion pairing is happening over there or no clustering is happening. Although the ion pair resides at 0.27 for a significant period of time, in the higher concentration in supercritical condition, fluctuation from contact ion pairing distance is still there. So that is why contact pair is less stable in higher concentrated solution in supercritical condition. So from clustering can result in different explanation altogether. So clustering can have different effect on the overall structure as to how we look at it. This is true even in case of if you take non-polar solutes also, which is not charged. I'd like to take any questions if there are.
Yeah, thank you very much for this wonderful talk. This is amazing. I mean, how much we can learn from a single diagnostic. Potential mean free, potential mean force, right?
Yeah.
Yes, are there any questions from people online? Yes.
Hello. Am I audible? Hello. Am I audible?
Yeah, you are audible.
Yes, ma'am. My question is, if I have a system like electrolytes, suppose I liquid mixture, so which type of forces that I should apply?
Your voice is not very clear. Can you please type it out in the chat box?
Suppose I have a system like electrolytes, or you can say ionic liquids. Okay.
Still, your voice is not very clear. Can you please,
Please come here.
if it is possible, you can type it out in the chat box, then I can reply.
That he is coming forward.
Okay.
So his question is that if he has ionic liquids,
Uh-huh.
and then we are giving him a separate
Yeah.
device to speak.
In case of ionic liquid, which kind of force will be?
Hello.
Which kind of force, in the sense you are asking about the force field? Is it the force field parameter that you are asking?
Yes, exactly.
Yeah, so in case of ionic liquids also, the previous ones like BMIM series of ionic liquids, OPLS force field works quite well. In case of choline based ionic liquid that I have recently I have done a study on choline based ionic liquids. So for choline based ionic liquids also, OPLS force field works very well. So again, it depends. You have to check with different type of force field available for each and every ionic liquid. You take only the pure ionic liquid, you perform one simulation for 1 nanosecond and see whether any experimental quantity you can reproduce or not from that force field. If any experimental quantity is reproduced properly, that means that force field is accurate for the system that you are trying to study. But OPLS force field works fine for all the ionic liquids as of now.
Right. Any other questions? Yes, we have from Kaushal.
Hello, madam.
Yes, sir.
So how you determine a dielectric constant in theoretical manner?
Using Gromax, if you just take the solvent molecule without any solute, in absence of solute, just do a simulation with the solvent molecule. And you have to perform it for a very long time. I mean, not 1 nanosecond, more than 100 nanosecond simulation is required. So if you do that in NPT ensemble, where you fix the number of molecules, pressure and temperature, you have a command in Gromax G underscore dielectric, G underscore dipoles. So that gives you the value of dielectric constant. In case of pure water, if you try to check, if you do it for say 10 nanosecond and all, the value will be around 63. Whereas water, the dielectric constant is 78. The moment you increase the time frame, you do it for a very long time so that your complete system is very stable, very stable, then you will see your dielectric constant reaches very close to the experimental value. It will not be exactly same as experimental, but it will come very close to that value.
Okay, because we are working on a liquid dielectric in experimental manner. So
Yeah.
yeah.
There is
Thank
one
you.
question in the chat box. GROMACS does it provide local structural or global? It provides global structural minimization. Local structural minimization, normally we don't, it cannot be done for a very large system using GROMACS. Normally for very small system, local structural minimization and all is done using DFT calculations and all. With GROMACS, you get the global minimization.
Right. Are there any other questions?
Yeah, if while simulation we couldn't get the experimental density, but see, there are many factors that can go wrong. First of all, you need to check for your force field. Normally, when we take any solvent molecules, for that solvent molecule, like for water example, there are many model of water available, starting from SPC, polarizable, non-polarizable. So many water models are there. So you have to check for each and every water model, that is the Forcefield parameter first of all, because for a different type of system, different type of Forcefield parameters will work. It's not like if you take one simple ion pair, then if SPC model of water is working, if you move on to some high temperature or low pressure region, the same model may not work. It may be different water model that you have to take. Then the time of simulation that you are providing. If you do a simulation for only 10 picosecond or 100 picosecond, 1 nanosecond, your system may not be stabilized in that time. It takes quite amount of time, at least 20 to 25 nanoseconds of equilibration has to be done. Then you will get the density closer to experimental. If still you are not getting, then you have to change your Forcefield parameters. Forcefield parameters also, you get it for different solvent molecules, different models are available. You have polarizable models, you have non-polarizable models, so you have to do a trial and error check over there.
Right. More questions? I have a naive question.
Yes, sir.
Let's say we have NaCl,
Mm-hmm.
Na ions and Cl ions. Now we are adding a solvent to it.
Yeah.
So there are possibilities that the reaction could be exothermic or endothermic.
Yes.
So how will we know? Is there any way to know? And what will
Yes,
be the
that
effect of the energy released? Or
yes, that you
yes,
can get if you are taking only whether you are taking one NaCl or you are taking a concentrated NaCl solution, you can calculate first the potential of mean force. Based on the potential of mean force, if you do a temperature dependent study, that is, if you are doing at 298 Kelvin, you want to know whether it is endothermic or exothermic, you perform two different studies at two different temperatures as well. One at 278, one at 318 Kelvin. The same system. Then you will get PMF at three different temperatures. At those three different temperature PMF, if you use, you can use finite temperature difference method to calculate the contribution of entropy and enthalpy. So at each and every point, at each and every distance, you can check whether your contact pair formation is driven by entropy, whether it is endothermic, whether it is exothermic. Based on the graph, you can calculate actually. Finite temperature difference method will give you all these results, whether it is endothermic or exothermic.
right. Thank you so much. And coming to the question, what Kaushal asked about the dielectric property. Dielectric, we understand it's because of charge separation.
Yeah.
So when we put solvent, so is it because solvent is coming between the ions, so we can see the charge separation is more and more, and we can calculate the average across all the pairs? Is it
Yes.
how it is calculated in Gromex?
Yes. Yes.
Right. Thank you very much. If there are no more questions, then let us thank Dr. Sonanki for this useful and wonderful talk.